All right. So, hi everyone. I'm Nick. I'm a final year DPhil student in the Genomic Medicine and Statistics doctoral training program. I work over at the DDI, Big Data Institute, with Cecilia Lindgren. My PhD involves genetics and obesity and genetics of outliers. If you're interested in any of those things, have a chat with me. Today, I'll be talking about variant association analysis, which is a central component of my DPhil. Yeah, that's about it. If I sound congested, it's because I am, so apologies for that. But yeah, we'll see how this goes. So, learning objectives for today are to understand the rationale and the methods behind variant association tests, and being aware of approaches to increase statistical power in this kind of realm of association testing. And then we'll also have a practical at the end, so you can get kind of hands-on experience doing burden tests. So to start off with, I think it's helpful to have like historical context to this subject. So in the early days of genetic association testing, they used family-based linkage and segregation studies. So here is a figure from a 1983 paper where they, this is like the first paper that found a genetic marker for Huntington's disease. You can see they're using this big pedigree, and they're basically showing, which individuals have cases, which individuals have disease, which individuals don't have disease, so cases and controls in a big family. This is a really powerful way to find associations for disease, but it depends on having this large pedigree and having multiple affected individuals, so having multiple cases in this family. It also has a couple of really key assumptions. So it assumes that there's full penetrance of the genetics on the disease. So as soon as you have a variant in a gene that's relevant to the disease, you will have that disease. We'll get a little bit more into penetrance later. And then it also depends on this very simple genetic model, which is as soon as you have genetic variation in a single gene, you will get that disease. So this is called monogenic or Mendelian inheritance. So a little bit more on penetrance. Suppose you have 5 individuals with disease-causing variants. If it's complete penetrance, all those individuals will have that disease, whereas incomplete penetrance, only a certain proportion of those individuals will have the disease. So again, to think about this another way, if it's fully penetrant, you will basically only see variants in a gene for individuals with the disease, whereas incomplete penetrance, you'll also see those disease-causing variants in disease controls, so people without disease. So if the disease is fully penetrant, you basically have this like perfect predictor for disease, right? As soon as an individual has a variant in that gene, they will have a disease. Whereas with incomplete penetrance, you now have to test for like the relative enrichment of variation in that gene in cases versus controls. So how do we put this into a statistical framework? One very simple way of doing this is looking at odds ratios. So the way you do this is you know whether or not an individual has a certain genotype, and you also know whether or not they have a disease. So you'll say a genotype is associated with that disease if the relative risk of disease is higher in people who are carrying that genotype versus those who are not. So you're just taking a ratio of cases versus controls, so A versus C divided by B versus D. And then you can also kind of flip this table around and show that this is equivalent to the ratio of A to B versus C to D. That's just kind of an aside. But this odds ratio only gives you a point estimate for how much of an effect this genotype has in disease. You also need a measure of like how confident you are in this association, right? So if you observe an odds ratio in a data set of 10 people, you could observe that same odds ratio in a data set of 1 million people, but which one are you going to be more confident in? It's a question to you guys. Which one? 1 million, exactly. So one way to get that is using, getting a p-value for your test. Very simple way to do this is Fish's exact test. They call it an exact test because it gives you the exact p-value for this kind of, it's called a contingent data, for this kind of scenario, A, B, C, and D. I'll also note that there are more modern methods for this exact test, but people will still use Fish's exact test. I still use it in my research as well. So you can do this in R. This is kind of a worked through example. Suppose you have this contingency taker. You can get a p-value for this, and you also get an odds ratio. And then you can also get confidence interval for your odds ratio, where see whether or not that confidence interval includes 1 indicates whether this is like a significant enrichment or whatever the answer to enrichment is. So if the confidence interval is greater than 1, that means it's enriched in cases and controls. If it's less than 1, that means it's depleted in cases and controls. Cases versus controls. Yeah.
Fish's exact test is non-parametric, right? So like, what kind of distribution does it use to get the p-value? Or
yeah, I don't think it.
I don't mean to get into like stats here.
Yeah. Not 100% sure. I think.
I'll do some Googling.
Yeah. I just go to the Wikipedia page and have a look. Okay. This is an example where the genotype is like fairly common in the data set, right? But what if you're looking at a genotype or a variant, let's say, which is only found in one individual. So this is a super rare variant. Well, what ends up happening is, this isn't always the case, but you'll often get a p-value which is not significant or is just less significant than if the genotype was common. Right? So the point here is that there's low power for rare variants, and it's compounded even more so when you're looking at rare phenotypes. So let's say you're looking at a super rare disease and you're looking at rare variants that are associated with that disease. You will have very low power. So something I want to impress upon you is that statistical power depends both on the variant effect size, and effect size here we're measuring is like odds ratio. This is just a point estimate. But it also depends on the frequency of both the variant, so the genotype that you're testing, and the phenotype that you're looking at. Okay. So, yeah, go on. Yeah, so it's basically making this table even more lopsided, is the intuitive way of thinking about it. So remember, you can just kind of flip this table around. It doesn't really matter whether it's the variant or the gene of the disease that you're testing the odds ratio for. But the idea is that having a rare variant is equivalent to having a very rare disease as well. We just kind of flip them around. Doesn't really matter. Okay, so this is called the trumpet plot, and I love them a lot. They feature a lot in our recent paper, but it's a little overwhelming, so I want you to focus just on the gray curves. And let's start with just this kind of these light gray curves on the edges. So the idea here is that if you keep statistical power constant, so you just set it at like 80%, as you get to rarer and rarer variants, you need to have higher effect sizes to be able to detect them. So as you get rarer and rarer, this on the x-axis is minor frequency, on the y-axis is effect size. As you get to rarer variants, you need higher effect sizes to be able to detect them, like significance in the data set. And then if you look at these other gray curves, so as you go from light to kind of slightly darker to the darkest gray, these correspond to different sample sizes. So as you increase sample size, this goes from 100,000 individuals to 200,000 to 400,000. You're doubling the sample size every time. You can detect variants with like smaller and smaller effect sizes. You're increasing the power by having higher sample sizes. Now, really, the key point here is that keeping power constant and, let's say, keeping sample size constant, as you get to rarer variants, you need larger effect sizes to be able to detect them.
I'm confused. You said you're keeping power constant, but your effect size is changing. You just said that the power is dependent on the effect size. So what did you mean by that?
Okay, so instead of calling it power is dependent on effect size, it's more like the likelihood that you find an association is dependent on the effect size. So, I don't know, statistical power, you set it at 80%, and then as you get to rare variance, you need a larger sample size to be able to, a larger effect size and sample size to be able to find that association. Does that make sense? Yeah, exactly. Yeah. So sample size is kind of shown with different gray curves. And that's the idea of like, if you have a really large data set, it's going to be easier to find, or you're going to have more power, but don't think of it as like this kind of power. You're going to have more...
Statistical significance?
Yeah, kind of. But that also relates back to statistical power. Yeah. I don't know, it's a tricky thing to explain, but just think of it as having more power at larger sample size. Larger sample size is better. Yeah. Anything else? Yeah, so ultra rare variants need to have really massive effect sizes to be able to be discovered. But then equally, like flipping it around, common variants can be found with really small effect sizes. And that's exactly what like GWAS studies have been doing, where you find all these common variants with really small effect sizes across the genome, which then points to these phenotypes being like polygenic. Okay, so why would we? Yeah. Yeah. Because this is effect size, it can be either positive or negative. And so if you could also just think of it as absolute effect size, like absolute value of the effect size, and it would just be one curve. But
That's
yeah, yeah, exactly. Okay, so why would we even be interested in studying rare variants? It's because variants that have a large effect on protein products tend to be rare. And it's because of negative selection. So imagine you have a lot of important proteins in your body. They need to be produced. If you have a variant that has a really large effect on whether or not that protein is produced, those damaging or deleterious variants, they're likely to get selected out of the population. And here's just a little figure that kind of shows this visually. This comes from the Nomad paper of 2020, where as you get to more deleterious or damaging variant classes, so at the highest level here is nonsense variants, which cause premature truncation of the protein. Those will have the highest proportion of variants that are rare, basically. So as you get to more deleterious variant classes, they're likely to be rare. It's just from the paper. I don't know. It's a measure of... Yeah, exactly. It's a little confusing because normally you think of it as just like, you could use math and it'd go the opposite way, but this is just their measure. Is more rare, yeah. But it's also important to note that rare variants collectively are very common. So if you look at an individual across the entire genome, you will find approximately 200 very rare variants. So they just call very rare as like allele frequency less than 0.1%. And this also comes from Nomad kind of indirectly. But you can kind of use this idea of rare variants being collectively more common when you're doing this genetic testing. So how exactly do they do that? The way we do that is with collapsing tests. So instead of testing individual rare variants, you can collapse across a region, usually like a functional unit like a gene, which then increases the number of individuals with that genotype. So you'd say like in a gene, whether or not someone has any rare variant, that gives them a genotype of 1. And if you don't carry a variant anywhere in the gene, that would mean you have genotype of 0. And so you're kind of boosting your the number of samples with that genotype. So if you were to put this, yeah.
So in that case, you're not choosing what the variant is. You're just saying if they have this variant, you get one. If they have any variant, they get one.
Yeah. But there are also ways to stratify the variants to make them more like, I don't know, to give them more information. So we'll get more into that. But does that kind of make sense? No.
What part of it? No, I just understood that you will eventually then categorize them. Is that what you meant? Or-
Yeah.
Okay.
Yeah. There's like a very basic way of doing it where it's just like any variation in the gene,
Yeah.
you classify as 1 or 0, whatever. But then there are ways to kind of make it a little bit more specific. Yeah. Okay, so now instead of testing a single variant, you're testing across the entire gene. You're kind of collapsing across all these rare variants, and you're boosting your sample size, and hopefully, or not sample size, but the number of people with the genotype, and in doing so, also boosting your power for finding an association. So now a couple different ways to do this collapsing analysis. The most simple way to do it is with burden testing. There are a couple different ways people have done it. But basically what it's saying is that if you have a variant in the gene, or like multiple rare variants, that will, all those variants will have the same effect on the trait, and the way you kind of measure your genotype is either, like the most simple way would be, if you have any variant in that gene, then that means you have a genotype of 1, and if you don't have a variant in that gene, you'd have a genotype of 0. Or you could have like, you count the number of variants in that gene, and that gives you like a genotype between, I don't know, 0 and 10 or whatever it is. Or you can weight each of the variants in the gene based on their functional category on their minor allele frequency. We'll have another slide on that later. But the key thing about this burden testing is it's very simple. It assumes that all variants are causal, and it also assumes that they all have the same effects direction. So it could either be all the variants are trait increasing, or increasing the risk of disease, or they have the opposite direction, but they all have the same direction of effect. Now, slightly more, I don't know, like sophisticated way of doing this potentially is it's called a variance-component test. Now this is looking at the variance explained by genetic variation in the gene. So this is bidirectional in the sense that it allows for variants that have either trait increasing or trait decreasing effects. And it also is a little bit more well-powered when the causality of the variants in the gene is a bit more sparse. So it doesn't necessarily assume that all the variants in the gene are causal. And you can see from the dates of these papers, this came after the burden test. So it's a little bit more complicated. Okay, so now people have been able to combine both. Yeah.
These are just both examples of collapsing tests.
Yeah.
Okay.
Exactly. And then people are able to combine both of these into hybrid tests. And the most important of these is SCAT-O, so this comes from SCAT and then burden testing. So SCAT stands for sequence kernel association testing, and then the O here is for I think optimal. So it's optimizing both the burden tests and the variance component tests. Okay. So, oh yeah, go on.
So just to understand, the collapsing tests are bringing different variants regardless of whether they cause an increase or decrease. They're bringing them together. Then all these are just to improve the confidence of the test.
Yeah, the different ways of testing the genetic, different ways of testing the effect of those collapsed variants on whatever phenotype you're looking at. So a couple more considerations when you're doing this sort of gene-based testing. For many genes, you need to have a full loss of function variant to cause disease. But there are also cases where having just barely missense variants, they're not necessarily full loss of function, but just missense variants that impact a certain part of the gene. So it's important to separate, to stratify out these variants when you're doing gene burden testing to give you more power to detect the associations specific to each of those variance classes. So here are some figures from my own research. as I said, I do like genetics of obesity. Here we look at a couple of traits related to obesity, including like BMI, body fat percentage. And the idea here is that for genes that are truly associated with the trait, as you get to more and more deleterious variant classes, so as you go from like synonymous variants to missense to damaging missense to predicted loss of function variants, there will be this sort of monotonic either increase or decrease in the effect of those variants on the trait. Does that make sense? Yeah? Okay. But there are also cases where this relationship isn't as straightforward, which then suggests that you need to have this the specificity of the variant classes when you're doing this sort of association testing. So you can see here, there's the initial trend of going down as you get to more deleterious variants, but then suddenly the predicted loss of function variants have this completely different effect direction. And then here in KEEP 1, it seems that the damaging missense variants have more of an effect than the predicted loss of function. Yeah.
So these graphs are like in a gene and then grouping different types of variants together and then seeing what the effect is.
Yeah, exactly. Yeah. And then you can also consider other things when you're doing this gene burden testing. So you could weight variants by like how important they are, how likely they are to affect the phenotype. A couple different ways of thinking about that would be rare variants, probably more likely to be to have a higher effect on your phenotype. So you might weight rare variants more strongly in your testing. And then I guess a more intuitive way is like you can predict the deleteriousness of that variant in that gene. You might also weight the variants by deleteriousness as well. So one example of that is this paper where they looked at de novo variants, and you can basically see, they're weighting these protein truncating variants more strongly than a synonymous variant, and then missense variants are somewhere in between that 0 versus 0.81 weighting. And then for a given gene, you can calculate the gene score based on this weighting. For each individual, you take that average across all individuals, and you get a sense for like how enriched that gene is for damaging variation compared to all other genes. So you're getting like an average gene score, or an average score for that gene. You compare it to like the null distribution. Okay. So that was sort of the statistical methodology for burden testing, but there's also a really important aspect, which is the computational side of it as well. So there's this review paper from 2019 that said the main bottleneck for rare variant testing is the computational side, like the scalability to larger data sets. So I'll just go over two examples of software that people have developed to do this at scale. Yeah.
So gene scores.
How I think it's more like how important that gene is for a phenotype. Yeah. Okay, so two examples. SAIGE gene, and that came out in 2020, and then REGENIE came out shortly after that. REGENIE comes from Regeneron Pharmaceuticals, and they kind of have the same underlying approach. This two-step approach where the first step you're fitting a null model that you take in the phenotypes that you want to test. You take in like common variants that have been either really well imputed or come directly from like a genotype array data set. You fit that null model, and then in the second step you're actually doing the association test where you put in the genotypes that you want to test. So in this case it's like usually sequencing data if you want to look at rare variation. So it could be exome sequencing or whole genome sequencing. And this step 2 is where you're actually doing the genetic association tests based on the null model that you fit in the first step. A couple recent applications. I don't know, did anyone read the papers that I sent out about this? Did anyone read the first paper that isn't on this slide? No. Did you?
The one where we had to read specific paragraphs.
So there's that one, and there were a couple optional ones. Oh, okay. That's right. Okay, so there are a couple recent applications. I work with UK Biobank, so I'm just going to give all the examples that relate to UK Biobank. there are 2 papers on UK Biobank 450K exomes, one from Regeneron and then one slightly later from a group at the Broad. And then very recently there was one that was looking at pan ancestry gene burden effects using UK Biobank All of Us, which is a newer data set from the US, and then a biobank from, I think, Boston. But I'm just going to focus on GeneBAS. Has anyone heard of GeneBAS before? No. Oh, that's exciting. Okay, so GeneBAS, super cool resource. If you have your computer up, I'd invite you to just like bring it up and, I don't know, go crazy. Like look for your favorite phenotype or your favorite gene, and you can see like associations for, if you're looking at a certain gene, you can look at how that gene is associated with basically all the phenotypes in the UK Biobank. Or if you're looking at a single phenotype, you can look across the entire genome and see which genes are associated with that. They also have single variant association tests, and it's just like a really nice browser. Constantly using this in my DPhil. Okay. So, I think this is the last part of the lecture. When we're doing genetic association tests, you also need to consider the multiple testing burden. I don't know if you guys have covered this yet. You have? Oh no, okay. Good. So, genetic association testing, with the GWAS, you're looking at millions of variants, right? Or with a gene burden test, you're looking across probably like, I don't know, almost 20,000 genes across the genome. These are loads of tests, and you need to, it's like a slightly different framework from what a lot of other people are doing. It's like only a few tests, right? You're doing loads of tests. You need to be able to control the rate at which you're finding, you need to control the rate of false discovery. Basically it. So I thought of a fun analogy. We'll see whether or not this works for you guys. But suppose you want to find the best darts players in a group of 20 people, and you have this dartboard with a pretty large bullseye, and another constraint is you also want to avoid falsely labeling people as being good darts players for whatever reason. And you only allow each person a single throw. So you basically, this is 20 tests, and you're trying to avoid people randomly throwing it into the red bullseye, right? You're trying to avoid those false discoveries of people who are not actually good at playing darts. But how would you change this dartboard if you had to test 1 million people and you're trying to avoid false discoveries? Question.
Make the bullseye smaller?
Really? Yeah. Okay, so all you'd have to do is kind of reduce the size of the bullseye. And this idea is, it's called Bonferroni correction, Bonferroni adjusting your p-values. And all you're doing, super simple, you're taking your family-wise error rate, alpha, which is usually set at 0.05, probably already know that, and dividing it by the number of tests that you're doing. So if you had 1 million tests, you would just divide 0.05 by million. And this is exactly what you do in GWAS. Of common variance, usually people assume 5e minus 8. I don't know, anyone heard that p-value threshold before? Yeah. That's based on, actually, anyone know why we why we use 5e minus 8?
They explained it yesterday, but they didn't get into the reason.
What did they say?
Just that, like, for like GWAS studies, for some reason we use 5 times 10 to the minus 8th as our like threshold instead of 0.05.
They didn't say why though. Okay.
They said there's a statistical reason. That was it.
Okay. Well, this is yeah.
So if you take like a smaller value, like sample size, that makes it stricter.
More power.
More power, yeah.
Okay. Well, anyway, the reason why it's 5e minus 8, they're assuming 1 million independent tests. And the reason for that is at some point people were like, there are 1 million independent regions in the genome, and so that's why we have 1 million independent tests, even though you're actually testing millions of different variants, right? So one key part of Bonferroni correction is that it assumes perfectly independent tests, which is a very conservative, like overly stringent p-value threshold, because in reality, a lot of the tests that you're doing will be sort of related to each other. There are genes that are going to be related to each other. There are phenotypes that are going to be related to each other. So it's an overly stringent assumption. So another way to do this, and we're going to be very quick about this, is called like an FDR-controlled procedure, or a very simple way of doing that is the Benjamini-Hochberg procedure, where you take your p-values, you order them, and then you set an alpha, which in this case is going to be your false discovery rate, which is slightly different from your family-wise error rate. And so, sorry, K here is the index of each p-value. So once you've ordered them, it's just going to be 1, 2, 3, 4, 5, etc. That's your K. M is the total number of tests that you've done. M is the total number of points here. And then alpha sets the slope of this line. And all this is doing is saying, once you draw that line, what is the largest p-value, which is still below or on this line? So
Wait, can you repeat that? Because the line is based on those points.
the line is based on the alpha that you set, and also kind of based on how many tests you're doing. Yeah, I wouldn't worry too much about how intuitive it is. Just be aware of this procedure, and it has a pretty good Wikipedia page as well if you want to look at that. Yeah,
I mean, in that case, you
Yeah.
said it's
good question. People will do it different ways. So, I don't know. Usually you pick like a nice whole number, like 1%, 5%, 10%. But it can depend on like what you're feeling, you know. Okay, so just to check your intuition a little bit, you've set this alpha. If you want to increase your FDR, like you're a little bit more lax about your study, you're okay with having more false discoveries, but also improving your power, like having a higher chance of detecting all the true associations. You might increase your alpha to be 0.1 or 10%. That increases the slope, and you're more likely to include more false negatives, but also potentially false positive or true positives. Yeah. So
this would be if your effect size is really small, right?
not necessarily. This would apply in any case. It's just these are two different ways. And let me just summarize it actually. Bonferroni, I'd say, is what most people will do, especially with GWAS and usually with burden testing as well. It's super simple, and the reason why people use it is because it's very conservative. So it's really tough for like a reviewer to say, "Oh, why did you choose Bonferroni?" You can just say, it was super conservative. You know, we're being really careful with our study. We don't want to falsely claim that these genes are significantly associated with the phenotype. We're going to choose Bonferroni. Whereas Benjamini-Hochberg, slightly more complicated, but it's actually not that complicated. People will just use Bonferroni because it's so easy. It's just like dividing one number by another number. But if you want to be really precise with your false discovery rate, use Benjamini-Hochberg, and you'll already be like ahead of 80% of the people in the field. Okay. Last bit, I'll go through this very quickly. Another way to reduce the burden of multiple testing. So careful with the word burden, but basically with genetic association tests, you're doing a lot of tests across millions of variants or tens of thousands of genes. One way to reduce that burden of having so many tests is by combining some of those p-values, some of those tests together, using this kind of magical test called the Cauchy combination test. And I won't go into the specifics of it, but I'll give you an example of how you'd use this. So suppose you've done all this gene burden testing across the genome for roughly 20,000 genes, and you've done it for 3 different categories. So now you have 60,000 tests. You could just combine these into a single p-value for each gene using the Cauchy combination test, and it's usually like pretty well powered. Not quite the same as taking the minimum p-value across these 3, but kind of similar to it. And so this is one way to reduce, like, instead of having to do a Bonferroni correction for 60,000 genes, now you only have to do it for 20,000 genes. So you get a 3 times higher p-value threshold, and you boost your power. But you also kind of hopefully you're kind of little cynical about this. Like, there are ways people can play with this to not kind of like the p-value hack, right? And kind of play around with their research. So just like be aware that there are ways people can use this for bad as well. Yeah.
Is this 3 times the p-value or the average of p-value for each of these?
The threshold would be 3 times the p-value if you're using Bonferroni correction. Be slightly different with F. Yeah.
So you combine.
Exactly. Okay. So to summarize, anyone have the time?
11.
Oh, perfect. Okay, so to summarize, when you're looking at rare variants compared to common variants, you have lower power to detect associations. One way to increase that power is by combining all these variants together, collapsing them by a functional unit like a gene. There are different ways that you can test these grouped units. So the burden tests or the different types of variance component tests, and then also the hybrid tests, which combine both the burden testing and the variance component tests. There are different software packages that you can do this burden testing at scale. And then it's also important to account for multiple testing when you're evaluating whether a gene is significant. Okay. And now we are on to the practical, but I think you guys are doing a costume competition first, or is that after?
It's a financial.
Sorry?
It's a financial.
During lunch. Okay. Cool. So, do you want to take a break first and then go to the practical? No.
Little break, tiny break.
A little break? 5 minutes? Okay. Cool.
No, it's gonna be hard. So
It's not that hard. Don't worry. Yeah. Okay. And if you want, you can have a look at these